Bismillahirrahmanirrahim. Today's topic is the cement replacement material. This is the topic comes under the contents of replacement of replacement of materials in concrete, and as we know that the main constituents in concrete are cement and aggregate. So in this part of lecture, we will discuss about what are the cement replacement materials. This is to be reminded, and this is to be understood that the cement replacement doesn't mean that all 100% of the cement will be replaced. Some of the parts, some of the portion of the cement can be replaced. So the materials that actually helps replacing cement can be said as supplementary cementing materials. So supplementary cementing materials are materials when used in conjunction with Portland or blended cement contribute to the properties of the hardened concrete through hydraulic or pozzolanic activity or both. Supplementary cementing materials are added to concrete as a part of the total cementing system. They may be used in addition or as a partial replacement of Portland cement or blended cement in concrete, depending on the properties of materials and the desired effect on concrete. Supplementary cementing materials are used to improve a particular concrete properties, such as the mitigation of deleterious alkali aggregate reactivity. Today, due to improved access to these materials, concrete producers can combine two or more of these materials to optimize concrete properties. Mixtures using three cementing materials called ternary mixtures are becoming more common. Some of the common materials are listed below: fly ash, ground granulated blast furnace slag, silica fume, and natural pozzolans such as calcined shale, calcined clay, or metamorphic. During the course of this lecture, I will define each and every one for you. Traditionally, fly ash, silica, and natural pozzolans such as calcined clays were used in concrete individually as well. Now, what is a fly ash? Fly ash is a fine powder that is a byproduct of burning pulverized coal in electric generation power plants. Fly ash is a pozzolan, a substance containing aluminous and siliceous material that forms cement in the presence of water. When mixed with lime and water, fly ash forms a compound similar to Portland cement. The particle size in fly ash vary from less than 1 micron to more than 10 microns, with the typical particle size measuring under 20 micron. The surface area is typically from 300 to 500 square meter per kg. For a fly ash without close compaction, the bulk density can vary from 5 to 40 to 860 kg per meter cube, while with the close package you can have a density as much as 1120 to 1500 kilogram meter per cube. So it would mean that compaction of this would help in actually doubling the density of the mixes. The ground granulated blast slag, that is also known as GGPS, is a byproduct from blast furnaces used to make iron. Blast furnaces are fed with a controlled mixture of iron ore, coke, and limestone and operated at a temperature of about 1500 degrees centigrade. When iron ore, coke, and limestone melt into blast furnace, two products are produced: molten iron and molten slag. The molten slag is the light and floats on the top of the molten iron. That is the product we are actually interested. Obviously, the other the steel, that is obviously as a component, is a very component and essential part of the component. The molten slag composed of silicates and alumina from aluminium original iron ore combined with some oxide from the limestone. The process of granulating slag involves cooling of molten slag through higher pressure waters. This rapidly quenches the slag and forms granular particles generally not bigger than 5 mm. The rapid cooling prevents the formation of larger crystals, and the resulting granular materials comprise around 95% non-crystalline calcium aluminosilicates. The granulated slag is further processed by drying and then grinding in a rotating ball mill to a very fine powder, which is what we call GGPS, and that is what we use as our material. This is some of the pictorials of how GGPS look like. Another material that is used as SCM is a silica fume. It is a byproduct of producing silicon metal or ferrosilicon alloys, and it is one of the most beneficial uses of concrete because its chemical and physical properties. It is a very reactive pozzolana. Concrete containing silicon fume can have a very high strength and can be very durable. Natural pozzolans include rocks of volcanic origins, vitreous rhyolites from Rocky Mountain, this term you already know from your geology, as well as some sedimentary clays and shales. Some may be used as they are, while others undergo a process of thermal activation. Calcined clay, like, are amorphous aluminosilicate rich materials with local structures that differ from aluminosilicate network found in active grassy phases. Calcined shale is a heat-treated alkaline and then ground to fine powder, and the calcination temperature of 800 degrees centigrade was used. Finally, the inclusion of shale is also helped to reduce emission of carbon dioxide and revealed an ecological advantage for concrete containing a binder blend of cement and calcined shale. Another product of natural pozzolan is a metacoiling, is the anhydrous calcined form of clay, mineral kaolinite. Minerals that are rich in kaolinite are known as china clay, traditionally used in manufacture of porcelain. The particle size of metacoilin is much smaller than cement particle, but not as fine as a silicon fume or slags. Now, after a brief discussion of each of the material, let's see how those SCM differs in the properties or how they come up to the various expectations of concrete like water requirement, workability, and strength, etc. Let's start with water requirement. When the concrete mixtures is being added to fly ash, it requires less water, 1 to 10% less for a given slump than concrete containing only Portland cement. Now, if you lose ground slag, it decrease water demand by 1 to 10%, depending on the percentage of slag you use. The water demand of concrete containing silica fume increases with increasing amount of fume unless water reducer or superplasticizer is used. Natural pozzolans have little effect on water demand at normal dosages. When it comes to the workability of the concrete, which is very important factor of concrete, this fly ash, slag, and some other pozzolans can improve the workability of concrete of equal slump, while there's a problem with silica fume that reduce the workability and contribute to the stickiness of a concrete mixture. When we talk about how bleeding and segregation is affected, this can be for due to the reduced water demand. Concrete with edge generally exhibit less bleeding and segregation than the plain concrete. Ground slags with similar fineness may increase the rate and amount of bleeding with no adverse effect on segregation. Ground slags finer than reduce bleeding. About the setting time, fly ash, ground slags, and natural pozzolans will generally increase the setting time of concrete. Silica fume may reduce the setting time of concrete. The plastic shrinkage, silica fume concrete may exhibit an increase in plastic shrinkage cracking due to the effect of low bleeding characteristics. Proper protection against drying is required during and after finishing. Other supplementary materials that significantly increase setting time can increase the risk of the plastic shrinkage. The curing concrete contains supplementary materials need more proper way, more focus. This should start immediately after finishing. A 7-day moist curing or membrane curing should be applied. But if you are using pozzolanic materials, some agency has 521 days of curing, and this may be the disadvantage of using pozzolanic materials, and maybe this will impact the overall construction scheduling of a project. So some people, some agency or some contractors, they do not use pozzolanic material for the sake of rapid construction. So how does the SCM material affects the strength of an hardened concrete? All supplementary materials contributes to the strength gain of the concrete. However, the strength concrete, these materials can be higher or lower than concrete with only cementing materials. The strength gain can be increased by the one or more combination of the following: increasing the amount of cementitious material, adding high early strength cement, decreasing the water cement ratio, and increasing the curing temperature using an accelerated mixture. So how does this affect SCM affect drying, shrinkage and creep? When used in low to moderate mountains, the effect of supplementary materials on drying, shrinkage and creep is small and of little significance. With adequate curing, the concrete with supplementary material will reduce the permeability and water absorptions. Silica fume and other polymer materials can improve the chloride resistance under 1000 coulombs using ASTM C1202. The sulfate resistance and sulfate and seawater damaging effect can be reduced significantly by using silica fume, fly ash, and ground slag. The improvement can be reached by reducing the permeability and reducing the reactive materials such as calcium needed for expensive sulfate reactions. The improvement in corrosion resistance concrete can be achieved by reducing the permeability and increasing the electrical resistivity of concrete. Fly ash can reduce the permeability of concrete to water, air, and chloride ions. Silica fumes generally reduce the permeability and increase the electrical resistivity. So that concludes my lecture on cement supplementary material. I hope they are very simple to understand and I have delivered it effectively. Thank you very much and in the next lecture we'll discuss about aggregate replacement material. Allah Hafiz.